Hello, my name is Jeff Erickson. I'm at the OSU Health Science Center and the Neuroscience Center itself. I've been here for the past 23 years. And I'm going to talk today about some new molecules that we have developed that prevent hippocampal injury, in particular in the context of epilepsy. So I'm just going to read a lot of this with you. Epilepsy, 2.2 million people in the United States, and more than 65 million people have it. 150,000 new cases of epilepsy are diagnosed in the US annually. And 1 in 26 people in the US will develop epilepsy at some point in their lifetime. It's a significant problem. The major form of epilepsy is temporal lobe epilepsy, TLE. And the temporal lobe is basically in the hippocampus. The hippocampus also connects to other limbic areas in the brain. And it's the most epileptogenic region of the human brain. So hippocampal sclerosis is the commonest cause of TLE. And that means injury, chronic injury in the hippocampus. And it's estimated that it represents about 40% of all epilepsies in adult people. And the risk factors of developing this hippocampal sclerosis is, for example, perinatal injury, CNS infection, febrile seizures, head trauma, traumatic brain injury, stroke, or there's also evidence that there is some familial predisposition to acquired epilepsy. So if you look at the incidence of epilepsy in humans, you find that a traumatic brain injury, if you have a traumatic brain injury, between 1.5 and 53% of the people will develop epilepsy. If you have an ischemic stroke, 2 to 30% of people will develop epilepsy. A hemorrhagic stroke, 8 to 26, viral encephalopathies, 4 to 20%, malaria, 10%. But whether or not you get epilepsy following these conditions obviously would depend on the severity of the injury. And also there could be some predisposition, genetic predisposition to any of these conditions. We use a rat model. In particular, we use an excitotoxin called canic acid. There's another model we use in pilocarpine. We use the canic acid model. And in the rat model, when you give canic acid and get neural injury and seizures and things, 90 to 100% of these rats will develop epilepsy. It's actually the best model for temporal lobe epilepsy, a human temporal lobe epilepsy that exists. So it's the canic acid model of TLE. Okay, so let me explain how epilepsy happens. Typically in humans, by the end of the first or second decade, so when you're a kid, patients are present themselves or have a first seizure. Afterwards, most patients remain seizure-free, like within a week, for variable periods that could range from 1 to 2 decades, so they're living normally, or even longer. So this is like what they call a latent period, or the silent period. Okay, but eventually then, they develop these recurrent seizures that then start as adults. And that is what is defined clinically as having epilepsy. In the canic acid model of TLE, we inject rats with the excitotoxin canic acid to produce status epilepticus, which is a major seizure that lasts about 4 or 5 hours, or it's periodic, but they seize and then they recover and then they seize about 4 hours. Afterwards, the rats remain seizure-free for about 3 to 6 months, living normally, but then recurrent seizures start or restart. So most of the anti-seizure drugs are anticonvulsant agents, and they're usually given to patients after they have acquired epilepsy, okay, after the silent period. Many of the patients are either refractory to these anti-seizure drugs or become refractory after they have epilepsy and are prescribed this. So my laboratory has developed compounds that are not anti-seizure drugs, but are potential anti-epileptic drugs. Okay? And these kind of drugs, then you give 1 hour after you experience your first seizure, okay, before the latent period. And so basically, just some data that we have here showing at least the pathological changes. Basically, this is the temporal lobe, the hippocampal region. Is that the point? Well, anyway, glutamic acid is the major excitatory neurotransmitter in the brain, which is involved in learning and memory. But too much glutamate released from neurons kills neurons, like during a seizure. Canic acid. Canic acid causes excessive glutamate release from neurons in the dentate gyrus. Oops. Neurons in the dentate gyrus here that project to these neurons and those neurons in the CA3. These neurons then project to here. So massive excitotic release of glutamate to excite these neurons eventually kills them. This is after 3 days. And those are not vulnerable, and neither are those. Okay, so we look at nu-N staining to visualize this, but we also use fluorojade B, which is a marker that stains for degenerating neurons. And you can see that after canic acid, you see degenerating neurons in this region here where you see decreased neurons, obviously, right? Here's degeneration, and here you see the loss of the neurons. So this is after 3 days. You see that in sham animals, you see no degenerating neurons, and you see nice intact architecture of the hippocampus. In canic acid neurons, you see lots of degeneration, and obviously here correlates with that. Our drugs, this is one of them. You've given 1 hour after the status epilepticus, you have no injury or no fluorojade labeling, and you have now clean lines for your cell body labeling of the hippocampus. So SK378 is neuroprotective and a potential anti-epileptic agent. So in conclusion, we show that when given 1 hour after canic acid-induced seizures, our drugs prevent acute neural injury, normally that's seen after 3 days. So the question we now focused on is that we predict that these drugs are anti-epileptic agents. That is, we give the drugs 1 hour after canic acid-induced status epilepticus, and we predict that they will prevent the development of epilepsy during this rat model that occurs after 3 to 6 months after the first seizure. So basically, we know we'll look at inflammation, we'll look at microglial activation, we'll look at hippocampal sclerosis and injury. We predict that it won't happen. And once we prevent the acute neural injury, we predict that we'll prevent the chronic epileptogenesis that occurs to acquire epilepsy. So here's my contact information. So I guess you can just look up LSU Health Science Center, Neuroscience Center, you'll find it. But thank you. Yeah. I don't know if you heard me, I wasn't using this.
Yeah, there we go. You probably have gotten this question before, but have you tried to extend that 1 hour window, since practically speaking, getting something in a patient 1 hour, if it's their first seizure ever, may not be so practical. So what's the
Right.
belief that you have there?
We haven't looked at the therapeutic window of that yet. Obviously, that's important to do. But we wanted to first evaluate all of the compounds that we have to find out those that are protective and those that aren't. So, but we will look at that.
Hello, that was great talk. 2 questions. One is, are you injecting the drug directly into the brain at this point? That's one. And 2 is, what receptors or what are you targeting with this drug?
Right. So, so we're giving this IP injection IP. But we know that we've done some pharmacokinetics. And we know that it is orally available. I'm actually feeding rats that develop Alzheimer's now with this to see if it'll work under those conditions as well. So that's just fed into the chow. As far as what the target is, basically these drugs were screened on an assay that I developed and published in the Journal of Neurochemistry in 2017. And it's probably a transport system. It's not a receptor. So I haven't actually said in public what that is. Sorry.
Thank you.